Awesome, that's in. So just for those watching at home, new PowerPoint for this, good for 2 days. I've already downloaded it, so I'll just go in and start it. Maybe. All right.
You have to.
Oh, right. It's I tried to get sneaky. I was copying it out of the downloads folder. I was hoping when I moved it over, it would make a copy that was not restricted, but evidently not. Okay, we'll try this again. So anyway, this is a modified version, actually, of a couple different talks that I've given in the past. So Truth in Advertising, I'm one of the developers of this methodology. So this is kind of explaining one of my own techniques. So it's based off a lot of those kind of previously given things. This is going to be essentially for us, right? Proton computer tomography, ion CT. It's kind of a different way of looking at X-ray CT as far as you're concerned. Because on one level, we've just got a beam coming through, right? Ours is going to be particles. Traditionally, it's photons. It's going to pass through a body. And on the other side, there's going to be something that's changed. And we're going to use that change to figure out what it encountered along the way. We can do the exact same methods. We can do a back projection method. We can do iterative reconstruction. The only difference on ours, X-rays, we assume they go on straight paths. Not because X-rays travel on straight paths. Right? If you remember, we've already covered the physics for it, Compton scattering and all kinds of other stuff. But because we collimate it, right? Our detectors prevent anyone that scatters from being able to make it in. Now that also means that there's going to be anyone that was used for it that got Compton scattered can't be used for imaging purposes. So essentially you get dose with no benefits from all of those. In our case, we also travel along bent paths, but there's no easy way to screen it. In our case, it's bending all over the place. So there is no such thing as ones that you can find that were straight. So they're all bent. Therefore, we can't avoid it. So we're going to use bent paths instead of straight paths. And instead of attenuation, i.e. how many photons have been absorbed or how many of your things traveling through have been absorbed, we're going to use how much energy did they lose. But again, this is not really a problem. Pretty much all of ours are going to make it through. A small number out of, let's say, like, 200 million protons, somewhere around 10,000 will actually hit a nucleus and have some type of an interaction. That's really stupid small, right? And those interactions, even if damage is not really a problem, we're trying to smash things, right? So not really a problem with that case. But otherwise, it's basically the same. Now, why go over it then? Well, number one, it's mine, and I like to talk about it, right? So there's a little bit of just, you made something that's kind of cool. But the second one, which is actually more appropriate, if it was just an ego thing for me, I'd drop it. The bigger one is you're going to encounter stuff and variations of things throughout your career where you need to adapt. For instance, right, I'm going to talk over the basis of proton CT, but there's actually 4 different ways I can calculate it, and there's similar variations that I can do with an X-ray CT. So we traditionally do how much energy is lost, but we could also measure how much the bending occurred. So we can look at that. So we have, kind of an energy difference. We have an angle difference when they're coming out. That could also be a measure of how much stuff it encountered. But we can also count other things as well, right? One of the weirdest one, and this is something you can actually do with photons as well, is you can look at the distribution of energies that come into from a similar start angle and end angle. The analogous thing for X-rays is look at the standard deviation of a bin. Normally we just bin things up kind of histogram style and use that to figure out what's going on. But what if instead of just chucking them up and going, this one's in a bin and add them all up, what if we also calculated their standard deviations? How different were these things within a bin? Now something interesting happens, right? Because we discretize space, imagine there was just, for simplicity, two materials, one really dense, one really not dense. And that line didn't line up perfectly with one of your edges, so it went partway through one of your bins. You would expect that you get disproportionate across the width of the bin, i.e. for us, energy differences, right, things of that sort. We call this straggling, the spread of what's going on. And one side we would expect to receive very low amounts of photons because it was a dense material, right, or high Z. And the other one I'd expect to have just the exact opposite, right, of a lot of attenuation. I'd expect very little attenuation from the light material. That spread inside the bin tells me I moved along the edge. Right? Now, traditionally, this is not used. But it can actually be very helpful for finding out some basics, and you can redo this exact reconstruction for the idea of this straggling idea. Right? And that can help you get certain features much more precisely, right? We can get sub-bin now in our accuracy on where material boundaries are. That's kind of a nice feature, being able to tell where those boundaries are. And we can do an analogous type of a thing within a setup for X-rays as well. So my point being that there's a ton of different ways you can adapt things once you have an idea of, ooh, a little bit of extra information, how can I use it? So that's really what I want you to think about here, right? Slightly different situation. How can I adapt it so it can reach into the same area and then I can utilize it? Right? We're going to do another thing that's sometimes called list mode. We're going to track each individual proton. Could you track each individual photon? Maybe yes, maybe no, right? It's much harder, we tend to bin it, right? Because some get absorbed, so how do we count those type of areas, right? But if I had a wider ring and I found out that the photons ended up somewhere else, I could do some type of statistical spread. So maybe not individual photons, but I could look at a statistical spread of where photons were coming in from a particular direction. And I could do like a beam scan when I'm going through and try to track the regional areas and see what the spread function is. And that will give me a pretty good idea, because now that spread function is going to give me information about the Compton scattering. Compton scattering gives me information about the Z of the material. So I can actually figure out some differentials. My point of this is not necessarily that you're going to do that particular thing, but in life, you're probably going to take something and have a slight variant. Right? And so that's really what I want to cover in here, which is the idea, how can I look at something else and go, oh, I want to do the same exact thing. So this is just kind of a practical example of how you adapt it in. Beyond just this, what if I don't want to do X-rays? What if I want to do infrared, which is the most likely one we're going to do for our project? Again, a variation of computed tomography. We're just going to use a different wavelength of light, right? That encounters, in that case, a lot of scattering. Much lower energy. Right? So getting used to figuring out how to adapt things to a slightly varying situation is probably one of the more important skills that's out there, beyond the base knowledge. All right, so this is my acknowledgement page, because I said I kind of worked on this, but I by far was not the only one to work on this, right? You can see me kind of smack there in the original PCT collaboration. And then there's an extended collaboration. We start adding other people in. We've got tons of funding from all kinds of different organizations to do this. We've been working on this since the early 2000s, so we're 18 years in now. You know, it takes a while to build up a lot of this stuff, and we had to, you know, actually build sensors and everything else. So anyway, this is my thing to acknowledge. There's a lot more than just me involved. Okay, now when we look at this and we say new imaging modality, why do it, right? And you should always ask this question wherever you're at, right? I mean, on one level, you could always say, well, heck, it's knowledge, and knowledge is good, right? So that's actually a very true thing. When I first started my PhD, that was my first approach. Well, who cares, right? It was an unknown thing. Learn how to do it. Somebody will figure out how to use it in the future. Just pursue knowledge. As I've gotten older, I've realized, yeah, that's true, but not completely, right? Because I could pursue something that might take quite a while before it becomes discovered, and I could have pursued something different that would be useful earlier on. You know, sometimes you get a brilliant idea nobody else has, and then by all means pursue it, you know, to do things. In math, they don't really care as much, but we're not mathematicians. So for us, practicality is a big thing. So this question of why is important to us. All right. To answer this question, I want to give you a little bit of background. Now, part of the reason I think that you want the background history is I discovered that it was very hard for me to remember stuff if I couldn't tie it to some story that I actually cared about. And I find I care more if I know a little bit about the people, why the heck they did it. And if I know why they were involved and came up with things, then it's kind of fun and I remember it much, much longer with much less effort. So part of the reason I'm giving you some background of people here, number one, they did great stuff, but number two, it'll let you see why we care. So this is the first one we need to know, because we're going to talk about Bragg peaks and things of that sort. So that brings us back to this physicist, right? Won the Nobel Prize with his son. He's actually from Australia. Interesting enough, he went to London, did a lot of his study, went back to Australia. Interesting. One of my collaborators is at the institution in the town where he actually resided and did most of his work. And they've now got the first proton center in Australia in that town, partially in honor of him. But he discovered this, right? Bragg peak, we're going to show you in a sec, is going to be an energy depositing phenomenon. Most things kind of tailor off as they get further in. It turns out with charged particles, they have this spike at the end. And it's kind of a weird thing nobody was expecting. And so, you know, he discovered this kind of interesting thing that most of the energy gets dropped at the end before it stops. So in this sense, particles are very, very different. But that's not the only thing he did. I mean, it's kind of interesting. He did all kinds of crazy stuff. He got the Nobel Prize actually for a different thing. If you ever had to take like a materials course and they talked about crystalline structure and how they pack things, you might wonder how did they figure out where all these crystalline structures came from and what the basic structures, hexagonal, closest packed, and all this kind of fun stuff is. If you've never done a materials course, you just go blah, 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 cool crystalline structure stuff. But he's actually the one who figured out what the crystalline structures were. And he actually did it doing this area with X-rays. So he was involved in both X-rays and particles, a lot of the early studying. How do those particles scatter? And the scattering is proportional to the structure of the crystalline matrix, so therefore he was able to figure out what that crystalline structure was inside. Nobody else had figured out how to do this. He actually figured out crystalline structure. I mean, think he's getting down to atom level with, you know, technologies in the, you know, around 1900. So 120 years ago, think how crude stuff was. And he's figuring, I mean, X-rays is an idea have only been out for 20 years. And he's figuring out how to use them to examine the structure of matter at its, you know, one of its most low levels. Kind of a cool thing. It's kind of cool, too, that it was interesting enough that his son actually got involved. So that's kind of a cool project, father-son thing. Okay, why the heck do we care? Right? So here you can see the Bragg peak. Now what I'm showing you here, these are different, these are called depth versus dose curves on the left here. So imagine this is depth in tissue. I've got a tumor inside my brain and you want to hit it with something. Right? The dose is how much of that radiation you're going to get. So that medium amount of energy you're going to pump in at different depths inside the tissue. Ideally, I want it zero everywhere but the tumor, and I want the tumor to just get, you know, cooked basically, so that it dies off and whatever is most effective at killing it without alarming the nearby tissue, right? If you alarm the nearby tissue, you cause secondary cancers. Now you gotta, what is the right amount to do? But knowing what amounts you're gonna, how much dose you're gonna deposit is an important idea. Well, when you deal with an awful lot of particles, you'll see this kind of standard drop-off that goes on here, right? You know, and it'll vary. When you've got low energy X-rays, right? The kind of here they've got 200 kV, right? Ones, you can see it's kind of does this standard drop-off, which you'd expect exponential decay. Interestingly, when you get up to megavolts range or mega electron volts for these coming in, it's actually different. There's this kind of ramp up from nothing. So this kind of throws some people for you kind of, otherwise it looks like an exponential decay, but you expect it to go off like that, right? Well, in truth, it kind of does. It is actually dropping at that. What's happening here is sometimes called the buildup region. So what's going on is it's got so much energy that those photons actually eject the electrons, and they go travel. They're so energetic when they get hit. They travel a depth inside, and then they ram into stuff. So when you get the really high energy ones, way beyond just enough to eject it, actually the higher they go, the bigger this buildup region. Because think of it, right? Photons hit electrons, electrons travel a distance and smash into something. Right? Where it smashes in is the damage. Low energy stuff, it's not traveling far enough for it to be a worry. So the depth happens right there. But you'll get these other ones where it's high enough energy that it can go like say 3 centimeters deep into the tissue. Right? They're all being fired in one direction with photons. You know, the momentum preservation will carry that in depth-wise. So that's why this is called the build-up region. And this is why they sometimes call this effect, as you get to much higher energy photons, they call it the skin sparing, right? So it just means that early stuff, yeah, you got some electrons ejected, but that's not really going to kill anything. But the electrons come to rest somewhere right around here, and so that's where you really start seeing the effect of the dose. Okay? And then after that, you're getting into less and less energetic, so it's just kind of follows a normal curve after that. Right, so that's why the build-up region. Doesn't really matter unless you're going to become a doctor. Other than as an engineer, I always hate looking at something and not knowing why. But I know we do actually have one who's interested in doctor direction, so you actually have to know what's going on, or at least if you're on the medical physics side. So that's, you know, what's going on there. But in all cases, really, we're looking to the tumors. You got these exponential drop-offs. With electrons, you'll see it's actually really high and then kind of drops off. Right? So they've got a much smaller depth they can go towards. Not really useful for further in stuff, but if you got things near the surface, that's actually quite good. Again, think of these in terms of, we're not saying one is the right technique, another is the wrong technique. It's the right technique for the right area. Right? That's actually, we're trying to get tools. The neat thing about these, if you look at the Bragg peak, you can see it comes in. And what's the basic idea here is happening. When it's coming in, we're up in the 300 MeV range for most of our stuff. Right? 200, 300 MeV. These are traveling at a significant fraction of the speed of light. Right? They are traveling so fast. The way they interact is with that electron shell. Right? The electron shell is attracting them, ion coming in, so you get some bending, some curvature. Right? If you're traveling really fast, how much time do you have to interact with that shell? Very, very little. The faster you go, the less time to interact, which means the less you can actually interchange energy between them, therefore the less dose you do. As it slows down, it slowly builds up because you get more and more time. Once it drops below about, so this is kind of an argued number, right, of where exactly it transitions to start smashing into stuff, because it's not a smooth smashing area. everybody agrees it happens once you drop below an MeV. Most people say it's below 3 to 5. I've heard some people say that you should account for the effects as high as 10 or 20 MeV. My personal opinion, looking at the equations and having other stuff with this, is 3 is a pretty good boundary, so 3 MeV. But once they start slowing down significantly, they start smashing into stuff, right? Now they're going slow enough, they're no longer having overall tendency that's just getting bent slightly. Now it's kind of like one of those little pachinko balls, right? You drop the ball on the top and the array of pins and it bounces around. Right? In here, that's what it's doing. As it does that, it's smashing into all kinds of stuff. Lots of energy smashing into the pins, causing damage all over the crazy place, comes to rest. This isn't a perfectly flat line. For the same reason this ramps up. Because when it comes to rest, it hits stuff. And there's a scatter of secondary particles. So there's a little bit of a damage beyond there, but it's not huge. So there's actually a little bit of a trail off. But essentially, this peak and spread out one means we essentially start and say, okay, I want to get this dose here. And then you look at the difference to get to a peak there, right? Maybe you're down like this, right? So you have a line come in, you know, at like 0.1 or something that gives you the back peak. And then what's left of what you're trying to do for the spread out one, you then take as your new trajectory. You fit the next one over. So as you do it, you're stacking them up, and it stacks up a little faster on this side as you're moving over. Because you're kind of pushing this curve further and further. So later ones are going to be a little bit higher up on the spectrum because you have to start them at lower energy. But it allows you to get like a flat area. And this is generally, if you imagine this as your tumor width, generally a doctor says, I want, you know, so much gray in this particular area, let's say like 60 gray or something of that sort, which should be quite sufficient to kill most things, but it wants it pretty spread across that whole thing. You get, you know, well, I don't want to say you get too much higher, you have problems, because there's actually some special phenomena like flash that can actually be helpful in this, where you go to really, really high doses, but in very short time periods. But let's just say for a slower deposited dose like this, generally if you go higher, you're just going to cook the tissue more and more. And you want to kill it, but you want them not necessarily to get like a huge necrosis building up, right? So you want to build it over a more reasonable time period usually. Anyway, we want to take advantage of this, right? Because tumors usually happen inside. Here we go. You can see the effect over here. I'm trying to hit a tumor. We come in from a couple directions. Look how low the dose is on the entry beams versus where we're targeting some tumor inside. You can just see by the intensities of them, I'm able to put things where I want it to and essentially avoid creating excessive amounts of damage to somebody. Right? That's a huge advantage if you think this is your brain. Out of curiosity, anybody tell what view this is? But even just tell phase one. We're cutting it this way, that way.
Yeah, so it's left and right.
Yeah, left and right. Very good. Okay, now to answer that question of what's the problem, because essentially we don't want that depth curve off, right? If we miss it, that's can be really bad. Well, the idea of treating with this was first suggested by Robert Wilson. Anybody hear of Robert Wilson before? He's somewhat famous in these things because he's one of the people who worked on the Manhattan Project, right? Maybe a scary reason to be remembered. He started Fermilab, one of the major national labs dealing with accelerator technology and stuff just outside Chicago, Illinois. He's done a lot of stuff. He died in 2000, but he had the first idea of using protons for medical use back in 1946. So, yeah, that's kind of a crazy. I mean, just think World War II had just ended, and he's like, I bet you we can use these accelerators we were doing for all these other things and put them to medical use. So he had this idea. 45 years after that, the first center in a hospital actually opened up in Loma Linda, California.
So that's the group that I worked with, was the people in Loma Linda. But anyway, Robert Wilson's the guy who did it. And so
here's the idea of what's coming in, right? This is the second reason. So the first one is, why do we want PCT? Well, that peak, but if the peak is off, you get a high dose damage that's off, right? If it's centered correctly on the tumor, awesome. If it's missing, there's a part of the tumor that's cold, you didn't get radiation. There's a part of your brain that got hot, right? Got radiation, it shouldn't have. So we don't want that. The second one has to do with this radiobiological effect. Okay? So the idea of radiobiological effect is, remember we mentioned these things are hitting, they're causing damage. We want to think about what kills a cell. Let me ask you, what do you think kills a cell? Anybody got an idea how radiation kills a cell? What's that? It's DNA damage, right? So you can kind of get a hint because I've got pictures with DNA stuff in here and chromosomes, so it gives you a good idea that's probably where it is. This is actually what really happens, right? Because you damage with radiation, you know, something like a mitochondria, that kind of stinks, but you know, yeah, 1,000 more of them, so don't worry about too much, right? It's not the end of your cell. But if I damage your DNA and you can't repair it, when you go to split, two sides get damaged DNA, it can't run correctly, right? So the cell dies because it can't run correctly. You're basically burning up its running code. So that's the idea. There are two types of breaks, right? So think of DNA in your classic, you know, double helix thing. There are what are called single strand breaks and double strand breaks. So think of it like a ladder again that's been twisted. If there's a single strand break, that's like one little piece has been damaged, right? You could have a damaged section of ladder, you still got a ladder. It doesn't mean it's great, right? And if it's just damaged in one spot, the cell has things that will repair that. So the likelihood that a single strand break is deadly is low, right? Now, imagine I damage both sides of the ladder, a double strand break. How likely is that one going to get fixed? Well, you get pieces breaking off and all kinds of things. This is a much harder situation. And indeed, it turns out, even if the cell is able to do some repairs on it, it probably repairs it wrong and it dies anyway. So double strand break, highly deadly. So now we ask, well, what do each one do? Well, normal X-rays and gamma rays and things of this sort, they come in, they knock off an electron. Typically, you'll get, you know, now an ionized thing. Oxygen is the most typical one. That's you want to actually have that happen to. Decent amount of water and other things in your cells, so you get that, you know, oxide that's coming in, and that oxide now will bond onto some DNA, breaking the chain where it bonds on because it snaps the other bond because oxygen really, really wants its electrons. So it grabs that, and that causes a single strand break. If there's enough of them going on, you end up with a double strand break, and it dies. But as tumors start out, they're very light, they're really hungry, lots of oxygen, easy to kill them. Early stages, radiation, like X-rays, kicks butt on, you know, your tumor cells. As the tumor gets more mature, it gets denser and denser because it's growing super fast. As it gets so dense, it squeezes off the blood vessels. You know, blood vessels, guess what that means? No oxygen. So the cell goes hypoxic. Right? Your cells, believe it or not, can actually run in a hypoxic state. There is a way to do it. It's much less efficient. Usually it doesn't survive that transition, but if there's anything that's going to survive that transition, guess what it's going to be? Cancer, because it's designed to be highly survivable. So it is trying its darndest to do that type of transition. Okay? So it's able to survive that transition, and it runs in the hypoxic mode. Basically, the difference has to do with when you're generating your energy, right? So everything runs off generating ADP. There's two different in the Craig cycle. There's two different ones: an oxygen one that gives you like 42 per sugar, and a non-oxygen one that gives you 6. Right, so it's a question really of which one's more efficient, not can you live. So it can live on inside non-toxic stuff, unfortunately. Now that also means when you're dealing with X-rays and it's a late-term cancer, there's not much oxygen, which means even if you get them ionized, you're probably not getting the one that's going to cause those strain breaks, those oxides. Right, you'll get some that still cause damage, but it's nowhere near as efficient. Right, oxygen is pretty darn deadly. Right, so they call this oxygen enhancement ratio. If you've got oxygen, it kills more things, and in general, it kills about 3 times more with the oxygen without. But think of it this way: what that reverse means is it's only 1/3 as effective when you get to late-term cancers. Well, how does ions kill things? Smashes in stuff. It has nothing to do with the electrons, right? You might get some, that's kind of just an added bonus, but basically you're firing a cannonball, and really the ion you're passing in is going to do it. The heavier the ion you shoot, the more damage it does. This is why a lot of people want to move to helium and carbon. Japan has like 6 carbon centers. Because when they start doing it, right, this is a carbon ion coming in, there are just tons of damage it did. So I've done some work with people up at UT Southwest. This was graphics they produced. They're heavily pushing for the whole carbon system and everything else. You know, but protons, you get a lot more double strand breaks. This shows some here. It would be much less for X-rays. You know, it's fairly dense here, but it's dense as heck when you get the heavy things like carbon or oxygen. And basically, when it's traveling along, coming to a rest near that Bragg peak, it is just double strain breaking all over because it's like firing a cannon at a ladder. Right? The likelihood you're going to cause that double strain break are really pretty high. So, very, very damaging when it goes through. Okay, so that's what this one's talking about. You can see oxygen enhancement and relative biological effect. That's what those ones are for. LET is how much energy it is. This one, kilo electron volts, right? So this is looking specifically at photons when they go on. Yeah.
So does that mean like the proton is better?
Proton is way better. They're not showing it hugely here because they weren't pushing for protons. They were pushing for carbon, so they didn't want to draw it too nicely for it. Just know the bias of the people who are drawing the graphics. Protons, like heavier ions, will generate a decent number of double strand breaks, much larger than X-rays, much, much larger. Right? If you were really to do an honest job of X-ray interactions, you wouldn't be able to show across these cells this many breaks for a single photon. It's more like you get a break maybe per photon. Right? So it's very sparse. Like I said, for protons, you absolutely get breaks per proton. With carbon, you get a lot of breaks. So that's kind of what they're doing. It's a little bit exaggerated. This isn't reality. So I actually have an NIH grant that was just given that I'm doing with several other places, actually studying the clustering of these breaks and how can we predict dose from that. Because these curves for photons and such, this one is relative biological effect of this versus its energy. Gives you essentially your curves. So it's harder to tell for protons and for ions because of this tendency to double strand break. In any case, you combine these, right? It's highly effective. This is what I was mentioning about. Imagine I took the Bragg peak and I missed, right? So my tumor's here. I go a little bit long, right? Well, what it hit with high dose is some nearby critical structure. And so usually when we're doing this, we're not just, it's not like on your arm where you can miss and it's okay. This is inside your brain. I miss and you can't walk again, or you forget your family, or, stuff like that. So we really don't want to miss. We want to hit as accurate as possible. And I've tried to show for each one of these, I've copied the curves and moved them, just so you can kind of see if I'm off, how bad does it change things, right? So I've displaced it to the side. Doesn't really make a big difference, right? A little horizontal shift doesn't make a lot of vertical. And that's true with pretty much all of them. Some of them you can't really even tell for a small shift. But for protons, you can tell, right? What I needed got a significantly lower dose and what shouldn't get anything got a huge dose. So we need to be accurate. This, if you wonder if this happens, the one on the right-hand side is lung tissue. So lungs are notorious for this, right? Your lungs, you go from like kind of like muscle wall and bone, and then all of a sudden now you got this alveoli and air, right? So the uncertainty range becomes crazy as you go through, right? So here we're coming from the back, there's a tumor near the spinal column. Near the spinal column means I would like the protons, I don't want the spread. But I also don't want that to carry through to the front and cause radiation beyond. Now, that'll happen with x-rays too, but we're trying to avoid that. And in our case, the dose spread is pretty high, you can see, for some of these. All right, so I really don't want to damage your lungs and make it more difficult for you to breathe. All right, anybody got an idea what that is?
Stomach.
You?
Heart.
So-
So, the diaphragm.
Yeah.
Yeah.
So, but the point here again, right? I'm hitting the edge of your heart here as well. I don't want to damage your heart and cause, by hitting on this portion here, I can cause arrhythmias and some heart conditions. So you don't want to take care of cancer and then have a heart problem and breathing issues for the rest of your life. So getting the range correctly is really, really important. So that's why we want to do PCT, right? Essentially, we're going to image it with the same way we're going to treat, so we know exactly what it is, so we can calculate very accurately. If you use X-rays, just straight one energy X-rays, your error in depth can be up to it's varied by tissue thing, but let's say the brain, it can be up to 2 to 5 millimeters. Right? Now that may not sound like a huge amount, but this is your brain we're talking. 2 to 5 millimeters in your brain is not something you want to give up. Right? In your lungs, it's far worse, but then you've got that density differential. All right, so how can we build such a thing? So this is one of my collaborators, giving credit to people that's on here. He's the one who actually started the PCT collaboration. So he's a doctor at Loma Linda, and it's Reinhard Schulte, and he's essentially the one who has been pushing this whole project the entire way through. And his big issue, he came from Germany, and this has been kind of like his life's goal, has been to make this a reality, because he originally was just doing this as a physicist and then became a doctor, and he was trying to say, okay, how do we get this so it's accurate? So he was, when they built the first center, he was the first one coming in as a medical doctor and physicist, knew both sides, was trying to figure out, okay, how do we treat people? How do we do treatment plans and everything else? And he quickly noticed this depth problem. And so he's trying to figure out, okay, how do I fix it? And there's a problem with the X-ray conversion right around water. There's a big uncertainty range where your tissues around water. Aside from your bones, right? Most of it's hovering right at water, and that's where the biggest uncertainty is. So he's like, well, how can I figure this out? Best way is to use the protons themselves. So that was kind of his thing. So I've been working with him and others, but he's kind of the central person. And this is the design that our whole group has kind of come up with. So there have been a few other designs, but in competitions, I mean, that sounds like I'm bragging, but ours kicks everybody's butt every single time. So a lot of other designs have been put out there, and they just don't work as well. So this is the way that works. We have a couple arguments every now and then, how should we switch this? But we tried another configuration for the energy detectors, and we're coming back to the same one again. Because again, it just, even on ours, slightly alternatives, doing them vertically as opposed to row-wise, turned out it was much better to do it this way. So I'll explain some of the issues that come in. Essentially, we're going to have two trackers. Think printed circuit boards. that we just print traces on one side going horizontally and the other side vertically. And we have a very precise pitch to them. Right? So that any time a proton passes through it, it passes through the metal, you get a tiny, tiny current as it goes through because it interacts with the electric field. An electron gets knocked off the metal. You take that tiny, tiny current and you, I got hit. Right? So that's basically how it works. Yes, you can miss it. So it is possible each of these on the front of the PCB, it goes one direction, on the back it goes the other. That gives you an XY grid. We assume that at that thing it's traveling, like I said, speed of light. It doesn't vary very far, so we consider them from the front and the back to be essentially the X and Y to be the same point. It's possible to actually not hit me. Right? So to go in between one and to get a miss. It's very rare, but if we miss one, we throw it out. So we only do the ones that hit. So we get 2 on the front, right, X, Y, and on the back 2. It's traveling through air. There is some energy loss. There is some minor deflection in air, but it's really tiny in the range we're considering. It is way below the uncertainty, so we're not worried about it. So essentially we count that it's going straight line until it hits the object. Right? Not technically true, but so close for everything else, lost. Right? So from this, 2 points gives you a line. That's how we figure out the entry line. Same thing on the back. We know the incoming beam because we have an accelerator, and that accelerator will have a very precise energy and a tiny range around it. So for typically these are 250 to 350 million electron volts. It'll typically have a variation of say like 2. All right, so you know we're way below 1% most of the time. So again, that energy variation, the incoming beam, we know that energy within 1%. We measure it on the backside. What it does is it hits typically something like cesium iodine. So this is used also in X-rays and other things. Cesium iodine is one of those things that interacts well. Iodine's really heavy. If you remember, it's one of our big tracer ones. It interacts with things nicely, right? It not only does it kind of nicely in that it's big, but since it's got a bunch of transitions in the visible range, you get a lot of light when it gets perturbed by one of these radiations passing, whether it's a photon or a particle. So we call it a scintillator, right? Radiation that you can't see comes in, you get a whole ton of light for every single proton that passes by or other ion, right? So they light up. We just put some photomultiplier tubes, essentially detect the light inside those crystals, and we can read out the amount of light you get is proportional. We fire 1 proton at a time, so we can track them, a few nanoseconds between them, very fast readouts, and we're able to now predict. Typically, when one of these sees a tiny voltage on one of its inputs lines that's enough to be different, it'll signal everybody else. If front and backside both see a spike, we go at 1 all the way through, yay, right, on these detectors, and then we read the readout. The light does kind of drop off over time, so it does overlap each other. There's a chance for error, right? We'd ideally like something that the energy dropped off faster, but you also need to get a good amount of light. Trade-offs. Yeah.
So, do we have proton gun technology that's able to put out 1 proton at a time?
Oh yeah, we actually do this.
Oh, great.
So we're actually in testing. We've been doing testing for. We built this actual scanner. I'll show you a picture of it on the next slide. We actually started the testing on this in 2014. We built the scanner. We got the funding from NIH in 2012. I came to Baylor shortly thereafter. I had to fly back every now and then. We tested it at Loma Linda for a few years. That scanner has gone to Europe. It's gone to Japan. It's right now. I think the scanner is currently. I think it's in Chicago, testing at the Chicago Proton Center. But it's bounced around quite a bit. So this is an actual physical thing. It's done. There are hundreds of facilities we could use this in.
Okay. Because one of the things I was wondering about is if you had a bunch of protons, how would you be able to correlate the incoming to the outgoing?
So you have to slow the beam down, right? or you have to have improved your detector technology. Now, typically in an accelerator, it's going to release one at a time, right? It'll be like nanoseconds between them, right? But there are ways you could separate them out. So one of the ones that I'm actually pushing for on this whole thing is being able to, what if I got simultaneous hits, can I separate them?
Right.
By having a large number of detectors around each crystal, I can find out if there was different light sources, there'll be intensity differences along the boundary. So there are ways to kind of speed it up. Right now we can track a little bit over 1 million particles a second. So that's, we'd like to get to 10. 10 is full speed. So we have to kind of throttle the accelerators back in order to actually image right now. If we can get to 10, no problems. Okay. Does this make sense as an idea?
I have another question. So
Sure.
for the beam, you mentioned that the energy of each proton coming out is very consistent. Is it able to have a narrow physical beam as well?
Yes.
So would you have to sweep that?
So that is one of the, that's a very good question. So there are two different techniques for it. Yes, the beam tends to be very narrow, right? All the modern systems use an extremely narrow beam called a pencil beam, and then we sweep it exactly, just like you would with an old style TV, right? With an electron beam, you just use electromagnetics and you just literally sweep it and scan it like you would. You don't do that for modern things anymore, but if you've ever seen those big old tube TVs, that's exactly what they did. So electromagnetic deflection, and you just deflect.
Okay, so it is electromagnetic here, so it doesn't take hours.
Because electromagnetics will do a great job moving an ion.
Right.
Right? You can't do it with photons, right? Because photons not charged.
Right.
So you can't use that same magnetic field. But magnetics have a great effect on these. So charge plates make an EM field, and boom, we can deflect them quite effectively. On older systems, like actually Loma Linda, it was the first one that went in. It does not. It has a wider beam. Well, actually, it has a narrow beam, but they didn't have the scanning down yet. So then they have a spreader that spreads it out, and then you put a bolus on it, which you put very sharp. So imagine lead, like maybe about this thick, and then you cut the center to a particular shape you want. And they will make a different bolus for each patient that's on. That'll have a depth adjustment, so where you want it on. If you just want generally open, you just open up the whole thing, and you'll get a Gaussian curve centered in the middle of it, highest density, and then dropping off. So those actually, believe it or not, even though it's less sophisticated, it has a certain advantage to us. They're still not extremely wide. Typically, where the spread is happening is a few meters from where you're at. So to get a beam like this wide, for the imaging purposes, starting from a meter or 2 meters away is still a very tight angle range. But essentially with pencil beam, which pretty much everything built from now on is going to use pencil beams, you can assume you know exactly the entry point. So some people are trying to drop the front ones because when you're scanning, you kind of know where it's coming from, and it's really narrow. So why bother even put the front detectors on? Just do the backside. And as far as we're concerned, that's fine. Just turn it off, right? So, yeah.
Backing up a little bit to Sam's first question.
Yeah.
About how many protons are coming out per second. For this, so I guess for the sake of imaging, you said you needed to slow it down.
Yeah, just because our response time. The biggest problem actually happens in these energy range detectors to find out how much energy is at the end, because it creates light, and you've seen it with monitors. Ours are much faster than your monitor, but that monitor appears to stay on for a little bit. Everybody's done the digital logic course, right? So remember when you had to do the 7-segment display, and we turn it on and then we turn it off, but it looked like it was continuous. It doesn't flicker. right? Because you've got that kind of drop off of the photons. Even once it's all done, it continues to emit light because there's still stuff smashing around. In our case, that's on the order of tens of nanoseconds, but we're still at, at say 1 million of these, right? We're at the microsecond range between them. So if they're a little bit closer together, you figure they could be 100 nanoseconds apart in a worst case. We'd like to be able to have them 10 nanoseconds apart in the worst case, which with a mean somewhere around 100 nanoseconds, that would be like full speed. That'd be the 10 million. But
So is that
right now we can't respond that fast.
And then at what like frequency is like considered, or like what would it be in a therapeutic sense?
So this is, you wouldn't do this while therapy's going on. At the moment, the plan is not to use this during therapy. I want to actually use it during therapy, because I want to track all the therapeutic ones going through. But at that point, we'd have to be at the 10 million. 10 million is full output of an accelerator.
So is that gonna be a material science problem to get it faster?
So that's part of it, but there's also some, like I said, there are some things we can actually do. No two ones are going to be exactly next to each other because there is a repulsion between their charge, so they're close. If you figure even on a pencil beam, right, if you got two together, they're going to be more towards the extreme edges. So then the question is, can you resolve out that separation? The light is going to be regional, so, you track them, and if you track them over time, I know there was light here, I know what its drop off is, I know when the peak was, I can subtract that because I know the shape of the light curve.
Okay.
So that's my plan. Right now, that is not done. But that is actually my plan. So, but if you're interested,
I think I missed something
Sure.
between the. What was the transition between talking about like proton therapy versus like imaging? Because you're talking about how this device is not therapeutic, but you.
so the beam itself can be used for both.
Okay.
Right? And typically, most people don't image while they're treating. And the reason is, for most systems, you can't. This is true with photons and everything else. I would like to be able to image while treating for several reasons. How do you know you're hitting where you're supposed to hit? Right? How do you know how much dose you're actually getting there? How do you know how accurate it is? So, there are ways I could do image while treating to make adjustments. Imagine I want to go out to the lungs. I can now track motion of the lungs. We can turn the beam off in a fraction of a heartbeat. So there's no reason I can't be detecting and finding out exactly where your heart is as I'm treating you. Turn it on and off as it's going on, and I don't need a separate beam. So I don't have to worry about correlations between them to do some heavy calibration and hope it works out. So there are a lot of benefits that come if you can do it. Right now, it's kind of science fiction-y to most of the doctors. But, heck, we're engineers, right? It's not like this is that difficult of an addition. It's just more precision machinery on there. And then I can hit something that they really need that they don't think they can have. So, to me, that's what I'm trying to do. I essentially, and this is true for you, when you go out to find problems, you try to find out what do they really want. You find out what can I do now, and what can't I do now but that looks reasonable, that you know a trajectory towards. And you start moving towards that with advances. A bunch of the stuff that we're doing now was pretty much considered science fiction when we started, but we built it now. And we've had to develop a lot of different techniques along the way. So why should it stay still in the next 20 years? So what I want you to do is more think about them, and every time, so you're generating great results. That means you're doing the right thing, right? You're looking at this and you're saying, well, hey, how's that working? Where's that problem, right? So first you notice where the problem is, and then you try to figure out, okay, how can I then account for that? Right? So that process is what you really want to do. That's engineering at its core, right? So, very cool. Other questions?
Awesome. Okay, so this is the actual device. You can see here are our two detector ones. This big box down here, encased in solid material all around, is where our scintillators are to prevent light from getting into it, to cause pollution to it. This is where the scanning beam comes through. And you can see there's always a laser alignment. So this is a laser built into the room. And that tells you where the center line of the beam is. Right? Now the beam will move around, this laser doesn't. This tells you where the center of this big circle where it comes out of is. So that you know, we call that the isocenter. So that's kind of the center of where your treatment volume is, because you always want to line up whenever you want to that center. So whenever you're doing these, even in medical treatment areas, you'll see this even if you get CTs or MRIs, you'll go in, you'll see lasers in the room that they kind of lighted. That's to identify that center, the isocenter. That's where the best image comes from. And so you always want to put that on whatever you care about. So that's why they always have these lasers built in.
Would you need like a sagittal line as well?
Yeah, so there are. You can just see this one from where the picture is taken. So we actually have one on the ceiling, but the laser will be coming like right down the middle of those on top, so you won't see it. So you have both. That's coming in. You'll often, if you have like an optimal treating distance, you'll see the vertical. You can see here, that's that. You'll have lasers that mark that. Here's where the start of your, right? Your treatment. You don't want to be closer than this, and they'll have one on the back. You don't want to be further than that. So they'll give you all kinds. There's lasers all over the place whenever you go into these. They're all design line lasers, very precisely calibrated, so that you can line up, in our case, for research and for doctors to have their patients lined up. But yeah, fun stuff. Okay, just another view of it. This one is towards, oh, there should have been another slide in between there. Anyway, this is what I'm saying, the start of our practice that comes in. So I'm hoping I upload the correct version of this. Otherwise, we might be short a couple slides. But it's just format stuff. So this right here is a bunch of blocks. If you notice, see how there's kind of like some, looks like color variation? These are blocks that you can add in. They're very precisely cut pyramids on here. We call them wedges. We use this for calibration. So when we do our initial area, we want to find out how well the proton beam and spec out their proton beam, how's it spread, all kinds of other stuff. So we start with just one block. We keep adding blocks, right, as we go through. And then we next go with just the diamonds and then add blocks to the diamond, so those pyramid wedges. And this gives us between one block width that's in. So we want at least one with just the straights, and we want some of the wedges. And so there's a whole procedure you have to go through. But essentially, we're able to measure them. As an interesting note, see these looks like a stair step? If you look real close, you'll see there's a little. So these are stair step, because our original thought was, let's just get a whole bunch statistically at certain energy ranges within it. That actually ended up causing artifacts in the final image. Because what had happened is we very precisely got certain points, whereas when we smoothed it out, so the new ones are all smooth, we get a spread. So even though we're not as precise at certain points, the variance in between was huge in between those steps, right? So precision, high error cause these little faint banded rings of error to come in. Whereas when we had a continuous distribution, it may not have been as close, but it was consistent. So you didn't get this kind of clumping, which caused banded error rings. I mentioned that one because when you start out, the question is, hey, what's the right thing to do? You take a good idea, you take a guess, you try it, something happens, you trace it back to where the problem was, and you remove the problem, and now you do it differently. It's often been said, and this is one of the truest statements in engineering and design, if you're not making errors, you're not trying hard, right? You need to fail, and you need to fail early, and you need to fail often.
Because if you're not failing, you're trying something simplistic, right? Only if it's a ridiculous easy idea does everybody get right the first time. Right? If you're making mistakes and going through, assuming that you're not just making silly mistakes, right? It means you're discovering stuff. Anyway, oh good. So up till now, this is kind of the problem flow. So you can see the first part that's up there, that's what we've talked about before, the not coming away, right? When a proton comes in, we get the strip number. Remember, there's little detectors. And we get the energy. We convert it into a position. We do some statistics to make sure that this is a good proton trajectory that goes on. We don't want one that enters down here and exits over here, and like doing something like that. Because if it's doing some crazy type of a pattern like that, then what that tells you is it probably hit a nucleus, right? And then did some crazy interaction, went off on a ridiculous direction.
So it hit a nucleus in the front detector?
Somewhere inside the object or whatever else. But if it's coming in one way and it's not close to aligned, right? Even on you, we give it so much energy, it should pass through you with very little deflection.
I see.
Right.
So you're comparing before the body to after the body?
Before and after. The front, we call that the front and the back, right? Front detectors to the back. We really only want a few degrees of change. We're willing to take more energy, we're willing to take less angle. Because in general, if it's moving fast enough, you should be fine. If the energy is dropped down really, really low when it exits, but the angle is still fairly reasonable, then it passed through safely. So there's a little bit of an interchange on that. But in general, that's what we do statistically. So we remove things that were, nuclear. Sometimes you'll actually get protons that come out with more energy. Sounds weird, eh?
Right.
Yeah, that's because it didn't come out with more energy. You got a proton with more energy coming out. It could be right in line and you still hit a nucleus, and it just happened to fire one lined up, and the nuclear event propelled one of its own protons, called a secondary proton, really fast at your detector, right? There's a chance it could be well enough lined up that you count it, right? So we also have to watch for that little bit too high of an energy, right? Because in real life, things don't gain energy, right? So something wrong. The bottom half of this, it varies by what technique you're doing to do reconstruction, right? What's done over here, assumes that we're doing iterative reconstruction. What we do is iterative reconstruction most of the time. There is a group out of Europe that does filter back projection, right? There are certain benefits to that. The number one thing for theirs is it's really stupidly fast. The problem is that it's got a lot more artifacts and other problems to it that we can avoid. And we can do all kinds of other funny, cool stuff, and that's usually more of what our concern is. But there's a place for each. So I don't want to say no to one of them. But the side over here that I'm going to spend most of the time talking on will be an iterative reconstruction based on my assumption that that's what you want to do. If instead you were going to do filtered back projection, a few of the steps you have to do, calculating the WEPL. WEPL is water equivalent path length. We take the energy loss and we figure how much water would it have traveled through to lose that much. You're pretty darn close to water. So that gives us an idea how much of your tissue it went through as a basic calibration. That's essentially what we're smearing back. So we have to do that here. They have to do that there because that's our quote unquote energy loss. That's your, in AX equals B, that's the P. Calculating the most likely path, happens here. In this one, technically it is happening kind of in this zone here, right? We sort them based on it. We could do the MLP here or here. Usually it happens here for most of our stuff. We do it just in time. From our local group, there are other groups that pre-calculate it. It's a 6 of one, half a dozen of the other. I do think it is the right thing to do it at the last second, just in time. We calculate every single time. And the reason is we don't want to store it. Because it takes a lot of memory, to be very honest with you. And it's pretty quick to calculate if you do it right.
And then in their case, instead of just smearing back on a straight line, you get a curved line from this. You smear back on the curved line and then filter. I mean, other than the fact that it's curved lines as opposed to straight lines, filter bad projector at that point. You know, bin your data, smear it, have fun, right? You know, in our case, this is where we'll do our iterative stuff, but we have to figure out some other things first. So I'm going to pretty much assume we're going through the other one. Okay. Okay, problem set up. All right, DTT. So this is those first 3 steps I mentioned. This is a rig. Oh, that's why. So I have this picture here twice. I was wondering why I didn't see that previous slide before. I guess when I moved it down, I copied it instead of deleting. So you can see here again, you can see them labeled front tracker, right? You can see the T and V planes marked out. You can see they're reversed on here, and there's your energy detector. So by seeing who's there, he works up in Chicago, so this one is being set up at the Chicago Center because he's their medical physicist who is working with us on this. In any case, so that's kind of setting up that room when it goes in. But we use that calibration phantom. We do other ones as well. To do the center line, we also have a single wire that goes through, just like you do for x-rays. Remember a line that gives you your line spread? So we do a line spread every day. There's a bunch of different ones we'll do to calculate the statistics and what is the modulation transfer function for it. All right. Bigger stuff. How do we actually calculate the level? And along with this, this is how do you set up the basic problem. Okay, so imagine I take those 2 vertical lines left and right. Those are the detectors. Imagine the X and the Y, or technically to us it's T and V, because X and Y don't rotate, that's the room. T and V is the rotating one based on how the beam is traveling. But anyway, we take the area and we discretize it. We chop it up into little blocks called voxels. Right? This is just one slice of it. And you have an individual proton passing through. In this case, I'm not showing the deflection to it, but you can kind of see it travels through certain voxels. We mark those voxels. That's the ones that it's going to hit. So this is how we want set. And then over here, it's going to detect, here's my particle, and away I go. Okay. So let's talk about how we actually then do that. So this is a smaller example. Right? We're going to turn all these into rows. So the question comes up to a lot of people, how do you get a row? Because it's a matrix you're traveling through. So that's kind of what this picture is designed to give you. So I just color-coded the matrix. Right? So imagine that's your volume area. And again, it's just a 4x4 because that's, rather than drawing hundreds by hundreds, that's a pain in the butt to draw. 4x4 still works. And we just take them and then we turn it into a vector by just chopping up the box, right? This one is row-wise. You could also chop it up column-wise. You know, that's a convention. You just have to ask what people do. On ours, we do row-wise when we chop them. You measure an energy differential. That's what that energy detector, the energy gives you actually how much energy is in it. And then you know how much it started with, so the differential is one minus the other. And then you can calculate what the equivalent, if you have lost that much energy, what was the equivalent length it went through. The U.S. National Institute of Standards, NIST, calibrates this, and they have a super high precision, right? So they actually take volumes of water and pass protons through them. Because it's not just us who use this, nuclear physicists use it, all kinds of ones. So the water equivalent path is a really important standard. It has been studied to the umpteenth degree. We don't need to measure it, guess it, whatever. There is an exact one. So we just store that data table. We take that energy, we can look it up. There's a fit polynomial, so you've got like 5th and 7th order polynomial fits to it. And we take those energies and we figure out what is the water equivalent path. This is one row of the A matrix. It says the path it took. And this is the energy loss that should be. Right? X, what was in there. So, you know, the very first one, X, says what was the, in this case, it's relative stopping power of that particular voxel. The second one down in X tells the stopping power of that, that's in that voxel. And all you're saying is 1 times the first one's entry means count that stopping power in the equation that added up to that path length. In our cases, all of our voxels are 1 millimeter, and we assume it went straight through. So we're assuming a length of 1. That is absolutely, well, it's most likely true when it's coming in straight on. When it's coming on angle, it could be as much as 1.4, or it could be just nicking the corner. If it just nicks the corner, we don't count it, right? But the average of that whole thing would be somewhere around 0.7. So there is a slight variant on that one where you can get. So we will often adjust for it when it's on an angle to give it a corrected path length. Again, averaged. Does that feel good?
I have a quick
Yeah.
question there. You mentioned that if the path length just skims one of the boxes, you
Yeah.
generally don't count it. Is there a reason we, like, say,
Well, you could.
try to calculate?
So, yeah, no, you could. So you could calculate the particular area. Here I just showed if we cut it, I did it, because I didn't want anything.
Right, makes sense.
It's just for a simple picture. But in general, this is a very small indicator.
Right.
Now, I could theoretically go in and figure out what that exact path length is.
Right.
And then do an adjustment to it. So now the question is one of efficiency. Does doing that correction greatly improve the quality? It absolutely improves the quality.
Right.
The time that it takes and the cost right now is prohibitive.
Okay.
So this is one of those things, see, I don't want to say no.
Right.
Because in the future, as computers get faster, better, we parallelize things more, that's absolutely within the range.
Okay.
Right? And so that is the right assumption to make. Just at the moment, technology, it's too slow.
Okay.
And what we define too slow as, doctors will wait up to 5 minutes for this.
Okay.
So we have to be able to, from scan to image, 5 minutes. That is what we call clinical. So, yeah, these are great questions. So this is just a second example when you're looking through, right? You can see. And in this case, it's supposed to be right on. I think it's pretty dark close. But you can see I put the previous one here too. So you can see I'm stacking previous history, next history, coming underneath it. As we stack them on, each row is a different proton, and that builds what we call the A matrix. Right? Previous energy, new energy, as we stack these up, you get a vector, that's B, for AX equals B. But it's always the same X because the relative positions, you're just saying, do I count that, stopping power or not into this? Does that make sense?
Yes, so when we do this for real, are we gonna have to have the top box be 3-dimensional?
So we do slices.
Okay,
So yeah, it is 3-dimensional.
okay,
But typically the distance between slices is bigger than what you have here. So like if, this is a millimeter on a side, between slices, and this is true for x-rays and MRIs, it's typically 1.5 to 2.5.
I see.
It can be as small as 1, but it's usually not.
Okay.
So we have to leave that option. My personal preference is I think you get better images if you do 1,
Okay.
all the way around.
Right.
Because the longer, thinner one has bad aspect ratio and it lose calculation stuff.
Right, so sorry, one more question.
Sure.
If, for example, a proton gets bent into a different slice, its path?
Yes, no, we actually count that.
Okay,
Absolutely. You can enter one slice and go out another.
okay,
It's actually very common. Most, about 96 to 98% of the protons can go between 1 to 5 slices.
okay,
Because the slices are vertical.
right,
But it means it'll go like first 2, and then these ones, it'll still be in that path line, but these 2 could be in one slice and those 2 could be in the next.
okay. So it does, okay.
They'll all be together. We do the whole reconstruction in one big fell swoop.
Okay,
Right? So you have to account for those when it's in it, but you'll just pick. just like this is one slice, you'll then pick up the next slice. Right, so when you're doing multi-slice, it just goes more, slice one, first section, next section, slice two, next section, slice three, so on and so forth. And same thing, proportion on X. So,
Can you go over again what you were saying, like the last row being like the stop? You said stopping power limit?
well, these ones right here,
Uh-huh.
the energy,
Yeah.
right? This is the A matrix.
Okay.
Right? This is just a 2D example, right? So the proton that followed this path lost energy proportionally here. We convert that into a water equivalent path length, but I'm just putting energy here because I think it connects better in your mind. But all you have to, it's a straightforward transformation, right? So what we're saying is I followed this path, I lost this much energy. I followed this path, I lost this much energy, right? So if I multiply something that describes how much is the stopping power, this is our unknown, right? Times this, if I knew you'll lose so much energy if you touch the first one, you'll lose a different amount if you touch the second one, so on and so forth, right? You add up all that, it should add up to the energy loss of the overall system. Right? Since we don't know that X that's multiplying these, that's what you're trying to solve for. A times X equals B. Right? But when you're considering the system, right, X is what you're going to solve for in software. How do you get the A and how do you get the B? You only measure this one directly. Right? This comes from that scintillator at the end. These paths come from the position, entry and exit position, and then we have to calculate them.
Is the, when you do the path calculation,
Yeah.
are you, for the sake of simplicity, considering a linear path, or can you do curve?
You have to do curve.
Okay, great.
So it's linear through air. We'll project it to the boundary of the object,
Right.
and then inside we'll do most likely path.
Okay.
And we'll know where it entered into the object, and we'll show you how to do that in like 1 sec. We're actually at our time, but it'll only take a sec to show you this last part. Which, in order to figure out what the path is, I need to know what the outside of the object looks like.
Right.
It sounds like a catch-22, but notice, if I use the protons that don't lose any energy, right? Protons less than some tolerance, imagine they lose almost no energy. If they lose almost no energy, that tells you they just went through air. It means they missed the object. So here's the idea. Imagine I assume everything in the volume is part of the object. And then I got one of these protons that missed the object. Well, if it missed the object, everything along that straight line, it will be a straight line, right? So I checked that it's a straight line. I checked it lost basically no energy. I go, well, everything along that line had to not be object. So I can zero it. It wasn't in the object. I have some other one that went through, lost no energy. I zero everything along that line. I repeat that process over and over again, and since I'm shooting these from all different angles, you end up with a core that never has something pass through it. That's your object, and everything else is the air around it. Right? So this is how we determine the hull. What's the outside of the object without having to do a reconstruction. Now I could just take all the particles and just do a reconstruction, but that's a lot of time for very little benefit. If there's a small number that miss, we just use them to figure out what the object looks like. All right. Just to give you a quick picture, so here are some ones where it actually was done. I could do filter back projection and then just cut it at a level. But when you do it, the artifacts inside it, some string artifacts, make it very hard to cut. So these are examples with it, and they get a lot of noise. If this was off simulated data, so when there's no noise, everything's perfectly clean. When I have some, we get a little bit of noise. They get a lot of noise. So ours is much more noise resistant. We tried this, and when we did it the first time, so we call this space carving, we found out in real life, it blew out lines right through the middle. Have we got an idea why that might happen? Remember those nuclear interactions that were rare?
Because
it's going super fast and not
And
interacting with anything.
it's going super fast and it hits something. And it generates a secondary proton with a lot of energy that's going in the same line. That one gets detected, but since the nuclear interaction propelled that secondary with as much energy as the primary or more, it looks like it didn't lose energy, and there's a chance it's just in line. There's not very many of these, right? You can count them up. It was like under 10,000. That's what clued us in. We went, I bet those are the nuclear interactions, and it turned out it was.
So do you just do an outlier thing?
So then we have to find the ones that are the nuclear interactions that are on them, and you know. So these are both from real data. And so we were able to then take this one and we cleaned it up to remove those secondary nuclear interactions, statistical check, and we modified stuff, and you can see all the problems went away at that point. And we have not had any problems since. But that nuclear interactions, even though they were rare, we were just like, forget about them, right? It did have one bad effect for us, which was on there. So sometimes you throw things out, and then you discover later on it really didn't matter. And then you just go back and fix it, right? You know, it's not the end of the world. And then work like a charm. So again, these are just real data ones doing that exact thing. We'll pick up here next time. So great questions, everybody.